So, as you know well, we are facing our first midterm examination. So it's on April 4th, no, April 7th, 4월 7일, on the 대강당, 아시죠? And so I checked the POBIS and it says the exam is from 6 to 10, but so it's not 4 hours, it's 6 to 9. So, well, it has to be changed, but it has not been changed for a long time. So, but you have to remember it's 6 to 9, okay? Actually, I have not I have not made problems for the midterm examination, but I will try my best to. I try my best not to be so that complicated. So don't worry about it. Don't worry about it too much. Okay. Also, when the time comes, I will let you know by the PRMS, and I will tell you the detailed instructions on the exam. So, well, there's actually nothing that special. But, so keep your eye on the PRMS. So last time we talked about the projection. So what kind of projection? So it goes like this. This is my vector space in Rn. And suppose that this guy has been spanned by linearly independent vectors, so n linearly independent vectors from A1 to An. Well, and obviously you have to assume that n must be less than equals to dimension of the embedded vector space M. So in that case, we can define the projection map PV defined like this, and where A is a matrix. So this is an M by N matrix, such that each of these columns are these linearly independent basis vectors for vector space B. So since we are assuming that these vectors are linearly independent, so that means this is a full-length matrix. And I told you, even though I have not justified yet, but well, in that case, A transpose A is invertible matrix. So ATA inverse is justified. Okay, so in picture, so we are supposed to solve the overdetermined system AX equals to B. So this is my A, and in case B is not a vector in the column space of A, so like this. So in this picture, B is not in the vector space, so column space A. And this X hat is actually the so-called the least square solution of this overdetermined system. So B, if you project this guy onto the column space CA, then A times X hat is going to be exactly the projection. So, and in my previous lecture, I explained why this equation must represent the projection of the vector B onto the vector space B. However, I also have to give you the formal proof why this one has to be the projection. So today I will begin my lecture by proving some trivialities. First, I will show that this guy, this is B minus A hat, X hat. It must be perpendicular to A times X hat. Okay, how do I prove this? Well, easy. So all I need to show is this orthogonality of these two vectors. So I think I will need to take an inner product of these two vectors and see if the answer is indeed 0 or not. So A X hat inner product transpose B minus AX hat, then here I am taking transpose of this. So therefore, and transpose of AX hat. Therefore, I have to invert the order of the multiplication and take a projection. So take the transpose. So B transpose and A transpose transpose, which is A, and ATA inverse being transposed, and lastly A transpose. So this is AX, and also B minus AX hat. So I'll just copy and paste. Okay. Then what now? And this guy multiply by B and minus, and the same guy by this. Okay. Oh, by the way, so the inversion and transpose, they are commutative. So you're always free to change the order of these two operations. So this is what? So this is simply A transpose A, everything transposed, and inverted. And so then this is just A transpose A inverse. So taking transpose of this is exactly the same thing before. So B transpose A transpose A inverse, A transpose of B minus B transpose A transpose A inverse, and A transpose, and A transpose A inverse, A transpose of B. But you know what? So since matrix multiplications are associative, so I am always free to get rid of this parenthesis. So A transpose A inverse times A transpose A, so they just cancel out. So, and the second term actually turns out to be precisely the same as the first one. So, so it's just 0. Okay, great. So since we now know this inner product of these two vectors equals to 0, so they are perpendicular. All right. Let me go back to some example. So this is an example from our textbook. I am supposed to find the solution of this system. So clearly this is an overdetermined system. 3 unknowns are 3 equations and 2 unknowns. And if you take a close look of this equation, then I am pretty sure that the vector on the right-hand side cannot be the member of the column space of A. Why? Because no matter how hard you try, the linear combinations of columns of A, the last component of the linear combination of columns of A always equal to 0, right? And so it can never be 6. So I am sure that the right-hand side die is not a member of the column space. Now what? So in principle, there is no solution. But since we are trying to find the least square solution, what should I do? So do you remember? So in order to find the least square solution, then first you have to find the so-called normal equation. And how do you get the normal equation? Take a transpose of matrix A and multiply it to the both sides, then you get the normal equation. Okay. This is a solution. Well, taking transpose of this matrix, which is this, and I multiply this transpose matrix to the left hand side of the equation. And if I simplify everything, then so everything turns out to be just two equation, two unknown system, linear system. And this is my normal equation. And if you then all you have to do is, and everything else is just matter of computation. I guess you can easily find the solution of this. And turns out to be x1 is 2 and x2 is 1. Yeah. This is not a solution of the system, but this is a least square solution that minimizes the discrepancy between the b and ax hat. Okay. Okay. I want to prove this fourth statement. These are very trivial. So as long as you understand the material or explanations I have given to you so far, but try to answer each of these questions by yourself. Why is it true? Yeah, this one must be obvious. So if my vector B is already a vector in the column space, then even if you project it to the column space, but there's nothing to project because the B is already in the column space CA. Therefore, it has to be the B itself. Yeah, I know this is obvious, but well, this requires a little bit of justification. Just like this. B is a member of column space. This is if and only if this overdetermined system has a solution. Let me say C. Okay, so A times C is B. So these are mathematical equivalent statements. So taking projection, I have A times A transpose A inverse A transpose times B. Now, okay, good. So this B can be replaced by A times C. Okay. So this is merely A transpose times A and followed by C. But I have A transpose A inverse right here. So those two matrices, they just cancel out. So all I have is just A times C, but A times C is B. Okay. So good. So okay. The question number 2. Suppose that my B is an orthogonal complement of the column space. What do you think will happen if you plug this vector into the projection? Zero, right? Because if this is my column space and if my vector is exactly perpendicular to it, then even if you project it, then all you get is just zero vector. Okay. Okay, so again, the proof. So this is the proof. So B is a member of the orthogonal complement of column space. This is But you know, the orthogonal complement of the column space is the left null space of the matrix A. So B being a member of the left null space of A, if and only if B transpose times A equals to 0. Okay, and taking the transpose just one more time, then the A transpose B is the 0 transpose. Forget it. I will just get rid of the 0. Then P C A, and now I plug in this guy over here. Then A times A transpose A inverse and A transpose of B. But clearly this is a 0 vector, so everything just reduces to 0. So 0 vector. This is also very interesting one. Typically, when we are discussing the projection matrix, A is usually a wide matrix. Okay, m by n matrix. It's not necessarily square, but suppose that A is an invertible matrix. Then what do you expect from this projection matrix? I claim this matrix must be the identity. Why? Well, so usually projection implies you have the big ambient, huge ambient space, and you imagine just a lower dimensional subspace of it, and you consider its projection. And how do you determine this subspace? This subspace is determined by the column space of A. But in this case, A is invertible matrix. That means it has m columns and they are all linearly independent. Therefore, column space of A is actually the entire ambient space. Okay, so for any vector in that space, and you try to take a projection onto the space itself, then nothing changes. That means this map has to be the identity, right? Yeah. In other words, PCA of B is B for or B in R. Okay, agreed? This is the justification. A transpose A inverse and A transpose. This is my projection matrix. Usually, I cannot get rid of this parenthesis if my matrix A is a narrow matrix. But here, we are assuming that A is a square matrix and which is invertible. Therefore, I can get rid of this parenthesis and expand it by A inverse times A transpose and inverse times A transpose. Okay, so this is only the I can do this only because that my matrix A was inverted. Then you know what? So these two guys they cancel, and these two guys they can also cancel. So everything is identity. Lastly, if A is a column vector, then so what do I mean by A is a column vector? So usually when you say matrix, then matrix consists of bunch of columns. But A is a column vector implies A only has just one single column. So which is just m by 1 matrix. So in that case, this projection matrix is actually nothing but just one-dimensional projections we discussed earlier in the previous lecture. Okay, so this is my projection matrix, but here A transpose A inverse turns out to be just the magnitude of A squared. And this here, this A and this A transpose just turns out to be A transpose, which is clearly the Rankon matrix we discussed in my previous lecture. Okay. Okay. All right. Finally, I am ready to give you the proof of the statement that I promised one lecture ago. If and only if all columns of A are linearly independent. This is also, well, everything is very important, but I also regard this is one of the most important theorem in this lecture, in this chapter, because when we are discussing this projection matrix, then without any care, I just assume that this guy is an invertible matrix, A transpose A. Well, if my matrix A was the n by n matrix, then this is an n by n matrix. But not every n by n, not every square matrix allows its inverse matrix. But I just automatically assume that this guy has an inverse. Okay, but how is that possible? Because according to the theorem, this matrix is invertible matrix if and only if every column of A is linearly independent to each other. Aha. Just please allow me to go all the way to the beginning. So here, I always mentioned that these vectors are linearly independent. So, well, therefore, in other words, if this is not a full-length matrix, then this guy is not an invertible matrix. But so therefore, in order to avoid such an annoying scenario, so I always assume that these vectors are all linearly independent. Therefore, that implies this is a full-length matrix. Therefore, this one has an inverse. Oh, okay. So let me prove this. Hold on. So A was assumed to be m by n matrix. So therefore, the null space of A transpose A and the null space of A, they are both the subspaces of Rn, right? They are both subspaces of Rn, right? Now I need to show that these two guys, these two sets, these two spaces, they are actually the same set. So, well, typically, if you want to show two sets are the same set, then you have to prove the two-sided inclusions. So choose any guy from here, and if I can show that this guy is a member of this one, then I prove this sided inclusion. And if I prove the other direction, other inclusion, then we say the proof is done. Okay. Okay. Which side of inclusion is easier? Yeah, I guess this inclusion is easy. Choose any vector from the null space of A. So this means A times X is 0 vector. So multiplying the both sides by A transpose. again this 0. So that means multiply x to the right to the A transpose A, and the resulting vector is 0. So this implies x is in the null space of A transpose A. Okay, so the proof is done for this side inclusion. Now, for the another inclusion, again, I want to choose any typical element from the null space of A transpose A. Okay. Okay. Why am I stuck? Oh, sorry. So A transpose A times X is 0. Now, instead of multiplying A transpose to the both sides, now this time around, I am multiplying A transpose to the both sides of this equation. A transpose of 0. So this is just 0, not 0 vector, but scalar of 0. And this is what? This is just simply ax squared, the length, the magnitude of vector ax. But there's just only one vector whose length equals to 0, which is the 0 vector. So this implies ax is the 0 vector. So the proof is done. So the proof is done. All right. Now what? I have to show that these two statements are mathematically equivalent. Okay, just like this. Just consider the condition. All columns of A are linearly independent. Then this is if and only if Ax equals to 0 vector implies x equals to 0. Right? Because, well, this is our definition of the linear independence. But in other words, this one can be translated to the null space of A has only one vector, has only 0 vector only. Okay, but now we know that this guy is the same as the null space of A transpose A. So A transpose of A is the singleton set. Then that means all columns of A transpose A are linearly independent. But, well, there's only one difference. This may not be square matrix, but this guy is guaranteed to be square matrix. And square matrix has the full length. Being full length matrix means that matrix is non-singular matrix and it allows inverse. So ATA is invertible. The corollary. I guess this is the proposition that I tried to justify in my previous lecture. And I was not able to give you the proof, the official proof of this. I tried to give you the proof just by drawing some cartoonish pictures. But now I am ready to give you the official proof of this thing. How? suppose A is an m by n matrix, then we consider the dimensions of the null space of A transpose A. And since null space of A transpose A is the same as null space of A, so these two numbers must agree. But so how do you compute the dimensions? Then to compute the dimension of the null space, then that is the rank number of column number of this matrix minus rank of this guy. Okay, so and the column number of this one is n, and rank minus rank of A transpose A by using same reasoning. So this is column, it has the n columns, and its rank is A. And in order to achieve this equality, so you have to conclude that rank of A transpose A must be the same as the rank of A. Okay. What do you think of this? What do you think of this statement? True or false? Actually, this is true. Because rank of A is the rank of always the rank of A transpose. Okay, and because of our corollary, this is the same as A transpose times A transpose. Okay, so this is rank of A transpose. So if you apply this statement, this corollary, to not to A but to A transpose, then you get the same result. So so it's very good to know. So rank of A transpose A and A transpose A, they are all the same. Okay. All right. Okay. Before I end this section, so I have to introduce you some digression, but very important digression. Symmetricity and idempotency imply projection. Okay, what does it mean? So for any projection matrix, we can expect two important properties. So first one is every projection matrix must be symmetric. Let me go back to all the way to the beginning. So this is my projection matrix, A transpose A inverse, and A transpose. This is my projection matrix. And if you take a transpose of this guy, then you can easily check that transpose of this matrix is the same as the original. So therefore, every projection matrix must be symmetric, which is very easy to know. And also, what do I mean by idempotency? I guess many of you have never heard about the idempotency, but being idempotent means also if you have function and multiply, idempotency means the matrix multiplied twice equals to the same thing, equals to the original one. That is what I mean by idempotency. So in case of a projection matrix is always idempotent because, well, what if you compose two projections consecutively? if you compose two the same projections, then, well, for the first projection, then the vector is being projected onto the space, column space. But taking the second projection doesn't do anything, right? Just takes, therefore, composing two projections is always the same as just one single projection. So that is the meaning of the idempotence. And actually, I feel like if you believe in this big slogan, then symmetricity and idempotency, if you can find any square matrix such that symmetric and idempotent, then that must be projection matrix into its own column space. So this is something that I can even prove it. Okay. All right. So let me prove this. If P is a projection, then P is symmetric and P square is P. So P is symmetric matrix and P is idempotent matrix. A, so since A is projection, so I must be able to write a projection matrix P as like this. And I am taking projection. Then this is, well, just matter of computation. So is the same, is the original matrix. So projection matrix is a symmetric matrix. And now I want to show that this is a idempotent matrix. So this guy multiplied by itself. Well, and here ATA is now multiplied by its own inverse. So those two guys, they just cancel. So this is just a projection matrix. Okay. So idempotency and symmetricity, they are very easy to show. But the other way is somehow tricky. If I have an m by n matrix, if this matrix is symmetric and idempotent, then P is a projection onto is column space C of P. So I'm proving exactly the opposite. Okay, so, well, we are assuming that P is symmetric and idempotent. So we have P transpose is P and P square is P. Now, what I want to show is this guy transpose multiplied by matrix P is going to be the zero vector, the zero matrix. Zero vector. First, so okay, why is that? So B minus P B can be written as identity minus P, everything by B, taken transpose, multiply by P. But since taking transpose, so getting rid of this bracket, big bracket, so IT minus PT and P, right? You know, the transpose is always linear, so this is good. And B transpose and identity transpose is clearly identity itself. And also we are assuming that P is symmetric, so P transpose is P, and B transpose P minus P squared. Okay. Oh, hold on. P minus P squared must be the zero matrix. Therefore, this is a zero vector. So what I did was, okay, summarizing, I multiplied this guy. I taken the transpose of this guy and I multiplied to the left side of this matrix P. So this implies this guy, this vector, is a member of the left null space of P. Okay. Okay. What now? Yeah, I have to be a little bit careful. Oh, so now this time I'm gonna make use of the fundamental theorem of linear algebra. According to the fundamental theorem of the linear algebra, this matrix can be written as a uniquely as a linear combinations of BC and Bn. Here, BC implies the component of B that is in CP, and this is component of in the left null space. So, well, and this Rn, well, this Rn can be always written as a direct sum of the column space and left null space. And this is the this is direct sum. So therefore, this decomposition must be unique. And so B minus PB can be written as BC plus the column space component plus left null space component and minus P times B. And we know this everything belongs to the left null space. Okay. Now, okay. Now I got it. So, well, P times of B. No matter which, so it doesn't. So no matter which B you take, you have just chosen from Rn, but this vector is automatically a member of the column space of B, column space of P. Right? This is a member of the column space of P. And also I know this is a member of the column space of P. But this entire thing must be now it's also on a complement, which is the left null space of P. So in order this guy to be the member of the left null space of P, the only possibility is this columns, well, this column space component must be 0. Okay. Now I understand why this P must be projection. So if you plug in this guy to this linear transformation, and what it does is nothing but just dropping the left null space component and just returns the column space component. as an output. And in this case, I'm pretty safe to say that this is a projection onto the column space. Okay. 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 Great. Also, I have very important application. The least square fitting of data. Well, this is not just one of the applications. I guess this is the most important application in this section. Just let's just consider this hypothetical scenario. You guys are all the scientists, and you're trying, and well, you're conducting some experiment. Well, sorry, you're interested in two variables, t and y, and t is an independent variable, and y is a dependent variable. And according to the theory, and suppose that you know that y is actually the linear polynomial of in terms of variable t. So suppose that y is a linear polynomial of t. So in other words, y can be written as c plus some constant plus slope times t. So you are expecting the t and y, they are satisfying this linear relation. But the question is, although you know that they are in this linear, they're related in this linear way, but you still do not know this precise value of these two variables, the precise value of these two parameters, c and d. So in order to determine the precise value of the value of c and d, you conducted a series of experiments, just like this. Well, in this case, you conducted 4 experiments. The first experiment, T1, T2, and T3, and T4. And for each of these experiments, the was B1, B2, B3, and B4. So basically you got 4 points in TY plane. And now what you're supposed to do is find a line that find a line that describes your experiment. So find a line that best describes your 4 experiments. Can you find such a line? So what do I mean by a line describes your experiment best? That means, well, if this is, well, suppose that this is the line that tries to describe my 4 experiments. Then, and every experiment, you are always consider there is always a room for error. So there must be some sort of difference between the ideas of the difference between this line and this 4 experiment. And I say the sum of the lengths of each of these green segments as a error, right? So a line that describes my experiment best means is the line which minimizes the sum of the lengths of these green line segments. Can you find such a C and D? This is my question. this is the questions of the linear least square. This is the problem for the least square fitting of data problem. So, right. So this is our assumption. I have supposed that I have conducted an experiment. Well, number of experiments must be always, well, you cannot do just one single experiment, and you cannot predict the value of parameter C and D. So let me say the number of experiments is always greater than equals to 2. Suppose that I have conducted this n experiment, and I want to find parameter C and D that best describes the data. That means I want to find a parameter C and D that minimizes the lengths of the sum of the lengths of this green line segment. So what are these green line segments? Okay, to find the length of this guy, so I will need to subtract the y coordinate of this point by y coordinate of that point. Okay, but y coordinate of this point is very easy, given by experiment, which is b1. What is the y coordinate of that point? Y coordinate of this point is this is t1, comma c plus d t1, right? Okay, therefore the length of this first line segment must be b1 minus c plus dt1. Okay. Okay. So what is the length of the second line segment? Length of the second line segment is likewise b2 minus c plus dt2. Right? Now, taking the summation is b m minus c plus d t m everything absolute value. So, now I can mathematically state my problem. So I want to find C and D that minimize this function. Okay, so this is very typical multivariable calculus problem. So given some multivariable function, I want to find C and D which minimize this function. Okay, but I changed my mind. So why? Because, well, so we as a mathematicians, we actually do not very fond of the absolute values. Why? Absolute value behaves very poorly, especially in terms of differentiation. So instead of working on these absolute values, yeah, we just take the square of each of these terms. And I want to find value C and D, which minimizes this function. Okay, but that will do the purpose. Agreed? So I'm gonna say I name this guy E squared or error squared. Okay, so I want to find C and D that minimizes my error square function. All right. Okay. Taking a quick glance of this problem, so it seems it is nothing to do with linear algebra. I guess this is more like a problem that should appear in the multivariable calculus course. But however, this is actually very typical linear algebra problem. Why? I will introduce these three matrices. 1, 1, T1, T2, Tm. This is my matrix A, and my matrix X, or this by vector X, is the C and D, and vector B has all those Y components that appears in this experiment from B1 to Bn. Okay, then let us consider this vector B minus A times X. Then the first component of this vector, this is m-dimensional vector, and the first component of this guy is precisely in this one. And the second component of this guy is precisely that one. And it goes on and on and on. And if I take the length square of this vector, then this is precisely the error square function. Okay. So, finding C and D that minimize this error square function is precisely the same as finding the C and D which minimizes the length between the B and AX. Then, in this case, my C and D that minimizes error square function is exactly the same as the least square solution of this overdetermined system, right? So minimizing E square implies minimizing B minus AX square is the same as finding the least square solution X hat of the overdetermined system AX equals to B. Okay, so everything turns out to be just the least square solution. All right, so let me try to find the least square solution of this system. To find the least square solution of this guy, first I will try to write down the normal equation. AT AX is AT of B. This is the normal equation. Then what I have is the transpose of this guy, which is 1, 1, 1, T1, T2, Tm, and this guy times this guy is this guy times so this is the normal equation. Yeah, and this looks somehow clumsy, so I will try to make it look a little bit more beautiful. So this is my final version of the normal equation. So clearly this is a 2 by 2 system. two equations and two unknowns. Well, so if you can solve this equation, and I'm pretty sure that this is a invertible matrix because this is T1, well, they're all a bunch of ones, and T1, T2, Tm, they must be all different numbers. So these two columns, they are always linear independent. So therefore, this is an invertible matrix. And so therefore, you must be able to solve this for C and D. And the solution of this system is the number that you're looking for. Is the two parameters C and D that best describes your series of data. Okay, all right. This is very good to know and very useful. And well, maybe if some of you are interested in taking a career in statistics, then maybe you should be able to use that maybe at least once in your lifetime. Okay, all right. The orthogonal basis and Gram-Schmidt algorithm. You know what I mean by orthonormal vectors. A set of vectors from Q1 to QK is called orthonormal vectors if the inner product is either 0 or 1, depending on the indices. Okay. So this is what I mean by orthonormal vectors. Yeah, I think I already mentioned this earlier. All right, there is nothing new. But using orthogonal vectors, orthonormal vectors, we can play even more interesting ones. I have K orthonormal vectors in Rn, a set of orthonormal vectors. Then we consider a matrix whose columns consist of Q12, QK. So what is the dimension of this matrix? So each of these columns, they are n-dimensional vectors, and k such columns. So this one must be n by k matrix, right? Okay. What I want to prove is this. Q transpose Q is what is dimension? This is n by k. This is so k by n by k. So must be k by k identity matrix. Why? This is very easy. Q transpose Q is you take a transpose from Q1T to QKT. And by this So, well, therefore, so essentially, so inner product. So this inner product with this is which is 1, but this inner product with all the other columns must be 0. And same thing is true for the second row. So 0, 1, da da da, 0, and everything equals to 0, but the diagonal ones. So the answer is the identity. Okay. Uh, so we are interested in such matrices. So we are interested in the matrices such that each of these columns is mutually also normal vectors. So if and especially if such a matrix is a square matrix with also normal columns, we say such a matrix is an orthogonal matrix, orthogonal matrix. So yeah, so whenever I try to introduce the notion of the orthogonal matrix, so I feel like the name is not quite right because, well, if I were to give the name of this, then I think I named it as an also normal matrix because every columns are also normal vectors, but well, they call it orthogonal matrix. But well, don't be confused. Even if we say it orthogonal matrix, but columns are not only orthogonal, but they are also normal vectors. Okay. And there's a very important lemma, which says, suppose B is a left inverse of A, of a square matrix A. Then B is a right inverse of A. Do you remember the left and right inverse of matrix? So, well, a long time ago, so we discussed about the left and right inverse. A matrix B is a left inverse of square matrix A. That means B times A is the identity. Okay. Well, if A is not a square matrix, then the matrix may have the left inverse or right inverse, depending on the dimension. So if your matrix A is a narrow matrix, then it has the left inverse. But if your matrix A is a wide matrix, then it has the right inverse, but not both of them. But however, this lemma says that if sphere matrix A has a left inverse, then that matrix is going to be automatically the right inverse. Okay. So it just suffices to check just one-sided inverse. Then then it's going to be the regular inverse. All right. So therefore, A inverse is B. Proof. We suppose A is an n by n matrix. And also, because of our assumption, we have B times A is the identity. Also, I hope you remember, A has a left inverse which was if and only if all columns of A are linearly independent. So those two things were the same thing. And here, A is assumed to be n by n matrix. So all columns are independent. That means the rank of A must be n, right? Now, from this equation, I want to multiply A to the right. Sorry, A to the left. Then ABA is A. Then taking it to the other side, then ABA minus A is zero matrix. So in other words, AB minus identity is BA. Okay, so AB minus I, this is just one single matrix. This is one single matrix, and this guy times A equals the zero matrix implies that every row of this matrix belongs to the left null space of A. Every row of AB minus I is in the left null space of A. Okay. Okay. All right. So I want to consider dimension of this guy. Well, number of columns of AT is A is n. So therefore, n minus so dimension of this space is n minus rank A dimensional vector space. Okay, you know how to compute the dimensions of these four fundamental spaces. But also we know that rank of A is n. So this is zero dimensional vector space. So conclusion is this guy has only one single vector, zero vector only. Right? So every row of AB minus I must be the zero vector. So that leaves only one option. AB minus I must be the zero matrix. Okay? So A times B must be the identity. All right? Okay. Okay. Now, because of this, I have very striking corollary that can be derived from this lemma. If Q is an orthogonal matrix, then inverse of Q must be Q transpose. Why? Why? Because orthogonal matrix has also normal columns and square matrix. And if any matrix has also normal vectors as its columns, then Q transpose Q must be identity. Right? So therefore, if Q is an orthogonal matrix, then we know Q transpose is a left inverse of Q. Right? Now, however, since my Q is assumed to be the square matrix, therefore, Q transpose is not only the left inverse, but also the right inverse. All right? Therefore, Q transpose is precisely Q inverse. Okay? Okay, why is it so striking? Why is it so amazing to me? Because, so if you believe in this, not only Q transpose Q equals to identity, but Q times Q transpose is also the identity. Okay, in other words, every column of, so that means Q transpose is also the orthogonal matrix. If Q is an orthogonal matrix, then Q transpose is also a orthogonal matrix. That means every column of Q transpose must be also normal vector. That means every row of Q must be also normal vector. Well, for me, this is very amazing, surprising, because, well, so by the definition of the orthogonal matrix, so we only know that the orthonormality is guaranteed in this direction. But once you have n such orthonormal vectors, then this direction, the orthonormality of this direction is also guaranteed automatically. Isn't that amazing? No? Okay. If your answer is no, but there's nothing I can do. All right. Thank you for your patience and see you next time. Bye.